Valgrind is a set of dynamic analysis tools for measuring the performance of your C programs. In this video, I'm going to focus on one of Valgrind's tools, Memcheck, whose job is to look for problems with how we use memory. In particular, it looks for two kinds of memory errors: memory leaks, which are blocks of memory that we allocate but forget to free, and the use of uninitialized memory. Let's start with some background about kinds of memory leaks. In its error messages, Valgrind distinguishes between blocks that are directly reachable and those that are indirectly reachable. A block is directly reachable if there's a pointer in the root set that points at that block. The root set is the set of general-purpose registers of all your threads and all your memory space, including the call stack of all your threads. A block is indirectly reachable if there is a pointer to it that is inside another reachable block. If we just malloc a space and store a pointer in the local variable, that's directly reachable. If we malloc a struct that contains a pointer and then malloc something for that pointer to point at, the struct is directly reachable, and the block that the struct points at is indirectly reachable. Now, the Valgrind documentation also talks about interior pointers. These are pointers that don't point at the absolute start of a block. They suggest that these could be created a couple of ways. They might be because they are tagged pointers. Some systems use the fact that the bottom 1, 2, or 3 bits of a pointer are always 0, because they point at word boundaries, so they store other information in those bits. They might be pointers that were deliberately moved into a block, like when you walk through a block that has a sequence of integers. Or they might be a random memory that looks like a pointer. I tried for hours to create any of these, and I couldn't ever trick Valgrind into reporting the types of leaks that these would cause. My guess is that my compiler is being too helpful and preventing me from stomping on memory in the way that creates an interior pointer. If I could create them, then Valgrind would also report blocks that are possibly lost, depending on whether Valgrind thinks that the pointers are really pointers or not. This code is an example of leaking things that are directly reachable. We lost the block that Q points at because I nulled Q. Now there's no way to free it. But I don't even have to do that. I malloced a block and made P point at it, and then just never freed P. This is the error report that Valgrind gives me. It shows both blocks were definitely lost and tells me where they were malloced. That's usually enough to figure out what we've forgotten to free. This code is an example of leaking something that is indirectly reachable. We never freed stuff, so we leaked that, and the block that stuff's P field references. You can see in the error report, Valgrind knows that it lost 16 bytes that were malloced at line 18, so that is what stuff pointed at. Then it also knows that stuff contained a pointer that pointed to another 42 bytes that were indirectly lost. Valgrind can also give you warnings about using variables that haven't been given a value. Since C does not guarantee to zero things, uninitialized variables can cause intermittent bugs that are really hard to find. Sometimes the uninitialized value is so obvious that even the compiler can warn you that it hasn't been initialized. In this case, Valgrind gives me these errors. The first one is telling me that there's a condition, like from an if or a while statement, that is using an uninitialized value. That's happening in A to I, that is converting my integer to a string. That's outside of my code, so I won't spend a lot of time looking at that. I know that Valgrind will also give me an error where I used it. And that's what we see here. It's telling me that I used an uninitialized value when I called printf on line 33 of my main function. That value was created by stack allocation, which tells me that it's a local variable in my main function. I can also cause uninitialized value errors in ways that my compiler doesn't catch. In this case, I allocated space for some ints and used one without giving it a value. This case shows how smart Valgrind is. Yes, I still get that uninitialized value in a condition error inside the printf, and I'm still not going to focus on that. The uninitialized value warning shows that I used an uninitialized value in the colon printf. I can look at that line of code and see that empty is the uninitialized value. That's a little weird because I assigned empty a value. However, it also knows that the value that I copied into it was uninitialized, and it came from the malloc call at the beginning. That's pretty helpful. There are a lot of command line options for controlling what Valgrind does. Let's look at some that are the most important ones for memory checking. --leak check is an option that makes Memcheck look for memory leaks when your program finishes running. You can tune which kinds of leaks it looks at with the --show leak kinds and --errors for leak kinds options. Both of these options take a comma-separated list of definite, indirect, possible, and reachable. --undef value errors is an option that controls whether Memcheck reports undefined value errors. Valgrind also gives us some options that help with the diagnosis of the problem. If track check origins is set to yes, Memcheck will track the origins of uninitialized values. The origin can be a heap block, or a stack allocation, or some other miscellaneous sources. It's important to note that this can dramatically affect your runtime. It can halve Memcheck speed. I had this turned on for my examples, but because it can affect runtime, I don't usually turn it on until I'm tracing an uninitialized value and my first look around doesn't find it. Memcheck can keep stack traces for calls on malloc and free to help you diagnose allocation errors. The default, alloc and free, is that it will keep a pair of stack traces for each block. You can save a little memory if you choose alloc then free, where the various stack traces are all kept, but they aren't paired memory-free traces. If you're only worried about allocs or frees, but not both, you can select what you need and save even more memory and time. Malloc-fill is used to force malloc to fill the block it creates with a given hex number. This can be used to find some challenging memory corruption bugs. Since you know what values should be there, you can recognize when someone has unexpectedly overwritten them. There are also some options that control how memory gets allocated. You can use the alignment option to specify the boundary at which words align, and therefore where your blocks should start. It defaults to whatever platform you're running on uses, but if you want something different, you can specify it there. The value you give must be positive, less than or equal to 4096, and it has to be a power of 2. Red zone size can be used to add padding before and after each heap block. By default, Memcheck uses a 16-byte red zone, and it uses those to detect overruns and underruns, writing beyond the space that you're malloced. You can make this smaller, which would reduce the memory overhead, but could also make you miss detecting some errors. Valgrind contains a lot of other tools, but I use Memcheck more than anything else. I hope this introduction gets you started. Let me know what it helps you find and if you want videos on the other Valgrind tools.